All right. Hey, what's up, guys? Hi again, and happy Thursday morning. Hopefully, you're getting started right away on your Section 4.2 Day 1 homework problem set. I think it might be maybe a tad bit shorter than some of the problem sets we've had recently, which it takes some time. But anyways, hopefully, you get this done in less than 40 minutes. You see the problems again. Your goal is to be exposed to all this stuff. You're not necessarily supposed to master it. Definitely not master it right away by yourself. But that's what Jamboard's for. That's what asking questions are for. That's what seeking out help is for, and seeking out other explanations that might be out there in the world. Okay, so I got 3 examples I'm going to do for you today in case you're having trouble getting started, or just want to see some examples first, or maybe you had trouble in 16, 17, 23. You're watching this a little bit later. I wanted to remind you that, again, the list of any upcoming assignments, just so you can budget your time, kind of plan accordingly, and see what's coming up. The list of the first 5 weeks worth of assignments for the semester is here. So you can bookmark this, you can go to it. And if you went to that link right there, boom, there's a link repeated right there, you'd end up on this, which is kind of each week broken out. Here we're in week 2 of spring semester, and here are all the problems, okay? So you're gonna have to do all of these here. I think classroom exercises 10 and 11 don't take too long. You just gotta have to think of a scenario that fits that criteria. 1 through 6 are pretty quick problems. 16, 17, that's gonna take some time. We're gonna do that in the example video right now. Then 20, 22, 23, some algebra solving problems, and finally 25, which is going to be a proof where you're going to hopefully establish that a quadrilateral is a parallelogram. That's what this section was about. And it's this, right? Is a quad, let's put it here, is a given quad a parallelogram? So you always want to ask yourself before starting a section or starting section's homework is, well, what did that section attempt to teach me? What is the new information? What's the new content that I'm supposed to know now having watched the lesson video, taken notes, maybe read the section? And that is, right, without even knowing it here, these problems are going to have to be one of these at least, quadrilaterals given to us. We're probably going to have to prove it's a parallelogram or prove something about that, like prove that it's a parallelogram at some point, so that then we can use maybe one of the properties we know about parallelograms, right? One of the theorems we know about parallelograms to prove something else on that parallelogram. Anyways, we don't know this is a parallelogram yet, and this is ACFE. So this is what we're going to have to prove is a parallelogram, okay? This is a planar figure on the left side here because it's drawn out on the sheet of paper. There's no dashes. This is a spatial figure, right? Spatial figures. This is going to deal in more than one plane, so we'll do both of them here. All right, let's get that circling out of the way so we can get to it. So the nice thing about these ones, at least in terms of time management perspective, is the directions here on 16, 17 is to explain briefly. So that's what you got to do in 16, 17. So maybe this is late in the problem set. Doing the questions before this pretty quickly, okay? The questions before 16 should be pretty quick. A question like this should take you maybe 3 or 4 minutes potentially, okay? I'll explain it in probably 10 minutes each, but hopefully you get it quickly, okay? So you don't have to actually copy it on the diagram. Don't have to write the given and proof statements because this isn't a proof, right? It's not a proof. You are just gonna, they're trying to make your life a little bit easier saying, hey, explain, right? Explain using your words, right? Using bullet points, that's fine too, how you could prove that the quadrilateral in question is a parallelogram. This one here, one of our quadrilaterals is given to us. So of course I'd read my givens. I have this. Maybe I'll do what I need to do in green here for this. That means parallelogram symbol. So this is a parallelogram. So I don't know what this problem is going to be about, but maybe I'm sketching it out. Maybe I'm doing it. Maybe I'm not sketching it out. I'm just trying to eyeball it. I want to know that, for instance, that those 2 lines are parallel and those 2 lines are parallel. Because the opposite sides of a quadrilateral, if they're parallel to one another, then that's the definition of a parallelogram. So we'll know that's true. DE equals BF. DE, so that's way up here, okay? Tick mark there, and BF is here, tick mark there. Okay, so we don't know of anything about this right here, okay? Except it's congruent to itself. Okay, it's congruent to itself. That might come into play. I don't know. But we know that that is congruent to that. We're probably going to use that at some point. We have that and that. Ooh, it's a parallelogram. Ooh, I see how it works. Do you see it, right? This is it. Like dealing with diagrams, getting used to diagrams, and trying to see it as best as possible. Okay, I have an approach, but that's just me thinking about it here. Okay, so let's see. I'll tick mark that because I got that. So I'd mark it up, right, to see if you can make some observations, see what you take. And then what's our goal here? I'm trying to get that the inside one is a parallelogram, and it's getting super messy right here. This is a parallelogram, right? I'm trying to get this being a parallelogram. And there are ways to do that, right? For instance, if I had this, right, opposite sides congruent, if I knew that, then yes, this would have to be a parallelogram. So we got that theorem this section, section 4.2, that if I have a quadrilateral whose both pairs of opposite sides are congruent, then it would have to be a parallelogram, right? So I think I can get there. I think I can get there. Okay, so let me back it up here. Let me maybe clear up this diagram a little more so we can see it a little bit more closely. Do you see it? Do you see it? Okay, I think the key thing is going to be this. I'm just going to mark up things and this here. So that the key thing is that you're given this. DE equals BF, so you're probably going to use that at some point. I thought maybe we'd have to do this and do segment addition postulate. I don't think we need to do that now because these here, look, what do I spy? I spy the fact that this is a congruent side on this triangle as this triangle. So if I can get that triangle congruent to that triangle, then that's going to help me prove the inside guy right there is going to be a parallelogram. Because how? Well, if that triangle is congruent to that triangle, then I could say this through CPCTC, right? If that triangle is congruent to that triangle, I can say that, and that's good. That's one pair of opposite sides of a quadrilateral being congruent. That's halfway there to establishing that it's a parallelogram. I'm going to get rid of that because I don't know that yet. But maybe we can get these triangles congruent to one another because I think we can. That's right, I think we can. How are we going to do it? Now I'm starting to second guess myself. Is this actually possible? All right, let's check it out. So we got that congruent to that. And now I can get an angle in this triangle congruent to angle in that triangle. How do I do that? Well, these here, DB is the diagonal of the larger parallelogram. So you know what? Because, and let me mark this up here, because this is a parallelogram here, maybe I'll draw it. I know that DA and CB are parallel because it's parallelogram, right? Ooh, I think I see it now that I marked it up. So I can get that angle congruent to that angle because these are actually alternate interior angles. Okay, those are actually alternate interior angles. Ooh, how's this puzzle working? So now if I can prove these congruent because I have two parallel lines cut by transversal, again, DB is the transversal, then alternate interior angles are congruent, so angle EBA congruent to angle FBC. Finally, what else is a parallelogram? What can we deduce from the fact that this is a parallelogram? Well, this side has got to be congruent to that side. So look at that. Here I would have an SAS. SAS correspondence. Those two triangles congruent, CPCTC, EA congruent to CF. A lot to keep track of here, okay? Could I do the same thing up there? I think I could. All right, so now I'm going to try to put this into words. You should try to put it into words too. But I'm going to explain how I do this, okay? So maybe I can put this into words. Maybe you can follow my reasoning. If not, and you're like, I got stumped on that one tomorrow. And even still stumped even if you look at it on the Jamboard here. But anyways, okay. First, I can say triangle. Well, not even first, right? I can. How are we going to prove this? I can say triangle DEA is congruent to triangle BFC by SAS. Okay, now I might say because DE equals FB, and that's given. Okay, I also know that angle ADB is congruent to angle CBF. Okay, and we go through, yeah, if two parallel lines are cut by trans, then ulterior angles are congruent. Okay, and one thing I might want to add on there is that since ABCD is a parallelogram, right? Well, we would have to say in a proof for that, we would have to say DE is parallel to BC. Okay, so that allows us to get that those alternate interior angles are congruent. And then what else? Because we did D, not, okay, I'm running out of space already too. Okay, so what have I said? I've said that, I've said that, I've said that, I've said that. I've even said that those are parallel lines, but I'd also say that the third part of the SAS is that DA equals BC because opposite sides of a parallelogram are congruent. By CPCTC, EA equals EC. What is that? EC, that should be an F. F. I'm talking about F's earlier? I am talking about F's. Good. F EA equals FC. And we're running out of space here, so this is kind of a little rough here. CPCTC gets you there, gets you there. Okay, and then I can repeat the same thing on top. Okay, and that I can repeat the same thing. Right, same kind of logic, which is with different parts names for triangle CED and triangle BFA. And then the key thing is CPCTC, EC equals EA. Then, geez, then, let's see, I gotta move this down. I gotta move this next thing down to make space. Oh, it's taking it with it. I don't wanna do that then. Then, ABCD is a parallelogram by, if a quad, if both pairs, I'm out of space here. If both pairs of sides, of opposite sides, are congruent, then it is a parallelogram. Okay, I ran out of space there. I'd be like, well, I can prove that this, right? I can get that, and I can get that. So hopefully you see it, right? Hopefully you see it. You don't have to write as much as me, but hopefully you can justify it. Maybe if I were writing this like as a student trying to do it quickly, is I would prove both two triangles congruent by SAS. You might even just say that, right? If you see it, that's fine. Like hopefully you can do it. And then, yeah, this triangle can do that triangle by SAS, and then CPCTC to get opposite sides, each opposite side of the quadrilateral in question. You can prove a congruence. This top one and bottom one we can prove a congruent because, right, this is parallel to that. So that means that these two alternate interior angles are congruent right here and right here. We're given EB, we're given D, and because this is a parallelogram, right, we know that side here is congruent to this side here. Anyways, messy. Let me go ahead and erase this. So just pose on that for a bit. Think about it. And yeah, that's that. Hard wordy. Let me try to word this one a little bit easier here on this problem. So let's see. We got to switch back to black, I guess, here. All right, given this, triangle ABCD and parallelogram, right? We deal with triangles all year, it feels like. So now we're dealing with parallelograms. Parallelogram ABCD. Okay, so that's that back one here. So this is three-dimensional. This is sort of like behind the screen. We got a parallelogram heading behind the screen a little bit, So when your diagrams are in color like this, so this was in black and white. We got something in red. We can ignore the red thing. But when it's shaded in color, that means this diagram is going to exist in more than one plane, right? We're going behind. This is going to have depth here. So anyways, we want to get that EBEF is a parallelogram, okay? I would know, for instance, triangle ABCD. So how would we do this? That is a parallelogram ABCD here. We got CDFE, we got that there, okay? So what do we know? Like, for instance, this AB is going to equal CD because opposite sides of a parallelogram are congruent. CD is going to equal FE because opposite sides of a parallelogram are congruent. So we're going to know that this and this. I can make that case by opposite sides of a parallelogram are congruent because I know this is congruent to that is congruent to that. So by transitivity, these need to be congruent to one another. So that's good. Now I have one pair of opposite sides of a parallelogram are congruent to one another. But do I have both pairs of opposite sides of a parallelogram are congruent to one another? Okay, can I get both? Well, I can't really, right? I can get these are congruent to one another. I can get those are congruent to one another. But that doesn't help me say anything about this side. and this side. So quick hints. What's maybe another way I could prove this? I can't get this. I can't, if you haven't seen it yet, maybe we can talk about it more tomorrow, but I can't actually get those congruent to one another. I can't figure that out. I can't crack the code. So then the question is here, if I know that, right, this is the quadrilateral in question we're trying to prove is a parallelogram. If I know that these opposite sides are congruent to one another, is there something else I can say? Is there something else I can say? Well, if I can get exactly one pair of sides of the, not exactly one, but one pair of sides of the quadrilateral congruent and parallel to one another, okay? So check it out. Maybe do green for parallel. This here, AB, is parallel to DC, right? Is parallel to DC. But DC is parallel to FE, right? Because that's the definition of parallelogram. So I would say that is parallel to that. I would also say that is parallel to that, right? Because these are freaking parallelograms in the back here. The question is, how does that help us get the front shape to be a parallelogram? Well, what do I have? What do I notice here? What did I end up being able to mark up right here and right here? Those sides, AB, those opposite sides are both parallel and congruent. And that's enough, right? Remember that came up in our lesson, right? Of trying to get a quadrilateral to determine it has to be a parallelogram. If one pair of sides of a parallelogram is both congruent and parallel, then that quadrilateral has to be a parallelogram. I think I misspoke a little bit on that one. If opposite sides of a quadrilateral are both congruent and parallel, then that quadrilateral has to be a parallelogram. Okay, so anyways, you gotta have to put that into words here. Let's see here. So maybe I'll just break it down to bullet points. AB is congruent to FE. And I might say opposite sides, parallelogram, congruent. And we had to use transitivity there, right? Because you have to do that if you're writing a proof. You'd have to do that for this back parallelogram back here, and also for this back right parallelogram here. So connect AB equals DC, and then DC equals FE, so therefore AB equals FE, okay? Two things that each equal the same thing are equal to each other, right? Transitive property here. Okay, so I can get AB's congruent to FE because of that. I can also get AB, that segment here. Notice this is going to be the same segment we have right here as we have down here. My next statement, it's going to be this, is parallel to FE. So notice those are the same exact. Those are the same exact segments. They're both congruent and parallel. And if two segments are both congruent and parallel, they could form a parallelogram. They have to form a parallelogram, right, by theorem. So the reason why you can get there is that AB parallel to DC, DC parallel to FE. That's your definition of a parallelogram. If you're just sort of explaining briefly, right? I wasn't brief here. I'm being more brief here. But if you're not doing it briefly, you have to say the definition of parallelogram. And then next thing, right? I can say therefore AB is parallel to FE, right? Which is what I said here. Because, and this goes back to chapter 2, ways of proving lines parallel, because if two lines are each parallel to the same line, remember that one? These two lines are parallel. So these two lines, AB and FE, are both parallel to the same line, DC, because they're in different parallelograms from one another, but they share that side. Then they're parallel to each other, okay? Two lines, if two lines are each parallel to the same line, then they are parallel to each other. And that, I think, is an A+, if I don't mind saying, answer to number 17, okay? So these are definitely trickier problems than I kind of thought, so hopefully you don't just toss up the question marks right away. Hopefully you give it a shot. All right, second one here. At least we'll do an algebra problem together. So you get another algebra example if you'd like. It says here, what values must x and y be to make quadrilateral JKLM parallelogram? So you have like, I think 3 problems like this towards the end. This is number 23, maybe just 2. But little algebra problem, right? You got to be able to solve equations, but also you need to know the geometry properties or geometric properties of a quadrilateral / parallelogram that would have to get applied here in order to solve the equation, set up and solve an equation. Okay, so if this quadrilateral were a parallelogram, okay, we want to make this a parallelogram. Okay, we got ML, right? That would mean that ML would have to be congruent to JK. And JM would have to be congruent to LK, which is right here. So these can be represented by the algebra we have in here. So ML, the length here is 5x minus 3y. The length of JK is going to be 3x plus y. Length of JM is 33. That's nice. We have one length here. And we have x plus y right here. Okay, x plus y right here. Okay, so what to me this is looking at is a system of equations problem, algebra problem. System of equations problem. So what a system of equation is 2 or more equations that share the same variables. Here we got x and y pretty much in everything. We don't have this, but we're going to set up an equation right there, right? So we know in order for this to be a parallelogram, then LK would have to equal MJ. So that means let's set up a freaking equation. X plus y has got to equal 33, right? That statement needs to be true in order for this to be a parallelogram. Another statement that would need to be true is 5x minus 3y would have to equal 3x plus y. Okay? Solving a system of equations, what I would recommend here is solve by substitution. Right? In Algebra 1, you study 3 methods for solving an equation, and I'm going to recommend solving by substitution in this instance. You could solve it a different way, but solving by substitution. What is substitution? That means isolate one variable and then to plug in to other equation, and then you should know what to do from there, right? If you've watched the last video on solving a system that we had just a few days ago. Okay, so what I'm going to do is I'm going to isolate a variable. Might as well isolate x right here. Okay, so to isolate x here, I'm going to take away y from both sides, and then I'm going to have x is equivalent to 33 minus y. If x plus y brought me to 33, then 33 minus y must equal x, right? X plus y brings me to 33. Take away y from both sides. 33 minus y represents x. So now I'm going to take this equation up here and I'm going to plug in wherever I see x, I'm going to plug in 33 minus y right here. Oh, we got a y right here. I'm still writing y. Oh, we have an x up here. I'm going to plug in 33 minus y. And we got a y here. Let's put that in here. Okay? So, right, we're kind of combining equations right now. Oh, that's not in black. I want it to be in black. Let's put it here in black. 33 minus y. 33 minus y. So now, voila, we have one equation that we know has got to be true, right? Because this is a statement of equality here, right? These have to equal each other. X could be represented by 33 minus y because x plus y brought us to 33. So anyways, this is what we have here. Now we just have y in the equation. So we have an equation that only has one variable in it. What do you know from Algebra 1? You can solve something like this. It's perfect, okay? So let's do that. So here, right, I would distribute first, distributive property of multiplication over addition. 5 times 33, well, 5 times 30 is 150. And then add a 15 to it, right? It's 5 times 3 is 15, so that's 165 minus 5y minus 3y. 3 times 33 is 99. 3 times negative y would be minus 3y. And then we got plus y there. Okay, so we distributed, got rid of our parentheses. Now we can combine like terms and solve like you've done hopefully plenty of times in algebra before. Okay, so I'm going to take my negative 5y. I'm going to add, take away more 3y here. Maybe I'll collect my variables to the right side, actually, come to think of it. So what I want to do is that I have more y's here technically. There are fewer negatives. Look, we're at negative 8y here, negative 3y here. So I want to add 8y here because I want to get rid of this too, okay? Addition property of equality is we can add equal values to both sides of the equation, and our equation will be preserved, right? We'll still have an equation at the end of the day. So this is going to become 5y right here. Negative 3y plus 8y is 5y. This is 165. Here's where I'm going to move my numbers. So I'm going to take away 99, of course. So I use my subtraction property of equality. If I take away 99 over here, I can take away 99 over here. The equation remains balanced. And, we have another y right here. Look at that. So I had another y that I didn't combine. So I technically had negative 2y's over here. I added 6 to it. Sorry, I added 8 to it. So I would have 6y's up here. Okay, so I missed this, right? I missed that y right there. That plus 8y is 6y. And that's going to be equal to 66. How about that? 666. Oh man, no, that's an ominous sign right there. All right, divide both sides by 6, and I got 11 for y, right? I got 11 for y. All right, so in systems problem, right, you plug in the other equation and solve. Third thing would be to plug back in and solve for other variable, right? The variable you hadn't solved for yet. Okay, so what do we know from earlier here, right? JM had to equal 33. LK has to equal 33, but LK is represented as x plus y. Well, y is 11, so what is x going to have to be? It's going to have to be 22, right? So you can solve this equation. So one of these are the other equation here. X plus y equals 33, y equals 11. So that means x plus 11 equals 33. Subtract both 11 from both sides, and you got it. X equals 22. And there you have it. Another systems problem in the back. Hopefully you're picking that stuff up. I don't think I want to give you a systems problem on a quiz because that's not fair to people who haven't reviewed a lot of the Algebra 1 stuff recently, and or maybe you're in Algebra 1 right now. So anyways, there you go. Hopefully you get that done because it'd be great if you know how to do this, but no pressure on knowing to do that. Hopefully you understand this reasoning though. This writing is crazy, but hopefully you see it and you can summarize shortly for us how to do that. And that'll go up on the Jamboard on Friday. Have a pleasant Thursday. I will talk to you later. Email me if you have any questions. Take care. Bye.